Okay, so let's begin. So this class today is going to be on Euclidean geometry. So we're gonna do I'm gonna go over some like basic, or not basic, but like critical geometry tips that you'll need to know in problems, and then we'll do a lot of problems. Okay, so first I'm gonna go over like angles and circles because you'll see angles a lot in circles, whether it be like inscribed angles or not. Okay, so we know that, like, for example, wait, hold on, let me edit. So angles that like bisect the same chord, they have the same measure, right? So like if this is AC, B, B prime, then angle, which is going to be equal to 1/2 times arc AC. Let me make this a little thinner. Okay. And arc AC just means like the central angle that subtends minor arc from A to C. And then we also have, if it's like a secant angle, then we'll have this angle is equal to, this is beta, this is alpha. Then we'll have, see, like A, B, C. The angle BAC is equal to alpha minus beta over 2. Thirdly, if we have like a tangent line and an angle that subtends that, so this is point of tangency, then this angle gamma, this is going to be equal to 1/2 of like whatever this angle is. It's like theta. And then lastly, like if we have two chords, this angle theta is going to be equal to alpha plus beta over 2. And this can be like intersected at any point within the circle. Okay, I think that's like pretty basic, but okay. Let's see. We can do a problem. What? I spelled that wrong, but okay. Let's see. Which problem should we do? So we have, so let's do this question. So there's a circle tangent to this line and then a triangle. So this angle is 60 degrees, this is 70 degrees, and we'll call this point A, point of tangency B, CD. So find what is the angle measure of angle CBD? Anyone? And you can just like, if you know, you can like shout it out or like, did someone say 60? Hmm? That's 50. Yeah, 50. Do you want to explain how you got that?
So I was thinking like two ways, either like since angle ABC is 60 degrees,
Mm-hmm.
that would um I was thinking like and then angle BCD is 70 degrees. Um that plus like the third angle would equal 180 degrees to make like a straight line. So
Mm-hmm.
180 minus 60 minus 70 equals 50.
Great. That's very good. Another way you can think about it is like 60 subtends line arc BC, right? And then angle BDC also subtends that, so they're going to be equal. So this is also 60. So they make a triangle. So it's 180 minus 70 minus 60. Okay, very good. Let's move on. We'll get to like some more angle chasing questions later, but now let's do triangles. So again, like this is going to be like pretty quick. So I'm not going to go over like right, obtuse, acute. Like I'm sure you guys already know what those mean, but I'm going to like let's do like triangle centers. So if we have A, B, C, then medians are like lines from they're secants from vertices to the midpoints of opposite sides. Right? So like this is going to be the median from B to side AC. And it's a fact that they all intersect at one point. This point is called the centroid. And furthermore, like if they we usually denote the centroid with G, and we also have like so if this is A, E, B, D, C, F, then we have the ratios of the side lengths are all equal. So like AG to G's equal to BG over GD, which is equal to CG over GF. And this is 2 to 1. Right. Um, what else? So angle bisectors. So again, another triangle, ABC. The angle bisectors also intersect at one unique point, and this point is the incenter. So it's going to be the center of the circle that's inscribed within the triangle. That does not look very accurate, but it is. Okay. So we usually denote it with I. So like I is the center. Okay, and then there's at least one more. It's going to be in intersection of the perpendicular bisectors. And we denote this as O. So O is usually the circumcenter. And then this kind of intuitively makes sense because all like, what is it? So like all lines from the center of the circle to outside point, they like bisect chords, right? So like the sides of the triangle are kind of the chords of the circumscribed circle. So that's why the center of that circle is like perpendicular bisectors. So they're all like right angles. All right, what else? I guess we can also just do the orthocenters. So the orthocenter is the intersection of the altitudes. And this is very nice properties. But it's not like the center of a circle or anything though. It's very nice properties. Like for example, like the reflections of the orthocenter. This is kind of more advanced, but like reflections of the orthocenter over the sides also land on the circumcircle. Okay. Um, so let's do an exercise for those. I actually know these exercises are all proofs, so we won't do those. Okay, I'm gonna go over some things about areas. So, okay, so we all know like the area of a triangle ABC is equal to like if a side is A, then it's equal to this, right? Because if it's ABC, side lengths ABC, then it's equal to the base times the height to A and over 2, right? So like 1/2 base times height. But it's also equal to like AB sine of C over 2. A, so this is A, B, and then sine of C is sine of this angle. And if you know like what sine of C means, it makes sense because sine of C is height divided by B. So they're equal. It's also equal to the radius of the inner circle times the semi-perimeter. So it's like, okay, sine S is like A plus B plus C over 2. Okay, so let's do a quick example involving that. Um, let's see this one. So in isosceles triangle ABC, we're given that AB is equal to AC is equal to 4, and angle C is equal to 75 degrees. Find the area of ABC. And there's like a quick way to do this. You don't have to like calculate trig function of like 75 degrees or anything. Anyone? Okay, so we can use like this formula, right? Because this makes the third angle 30 degrees. This makes angle A 30 degrees. So we can just use that, and then we get the area is equal to 4 times 4 times sine of 30 over 2. Right? Sine of 30 is easy to calculate. It's 1/2. And so that equals 4. Any questions? Okay. I'll also be like posting all these slides. Okay. Oh, congruent triangles. So in questions involving triangles, it's helpful if you can find congruent triangles, which means you can like equate lines with each other, and then maybe like isosceles triangles will pop up because isosceles triangles are really nice, right? As we just saw. And then similar triangles for the same reason because then you'll get proportions. Parallel lines, um, if we have parallel lines and like a transversal, then like equal angles are really nice. Right? And then equal angles can often lead to similar triangles or even congruent triangles if we have lengths. And then perpendicular lines, they're like you can often find some like right triangles inside of them. And then you can use like stuff with right triangles. Okay. These may seem like very, what is it, like convoluted or like pulled out of thin air, but they're actually like very helpful and useful signs to look out for. And it takes practice though, but yeah, you should look out for those. Okay. Now we're gonna move on to quadrilaterals. Um, quadrilaterals. Okay, so first trapezoids. Two pairs, two sides, one pair of sides are parallel, and they're like the bases of the trapezoid. And then also like these angles add up to 180 because of the parallel lines. But yeah, another good thing about parallel lines is that you can maybe like find quadrilaterals. Um, Another thing is like if you connect the midpoints of the two legs, A, B, C, D, E, F, then you have like EF is equal to 1/2 of the sum of the bases. And this you can prove if you just like drop the altitudes. Um, yeah, and then if AD is equal to BC, then the trapezoid is isosceles, and then you have a bunch more equal angles. So like this angle will be equal to this angle. Okay, let's do one question. Um, Actually, no, we'll just move on to parallelograms because we still have like a lot to cover. Okay, so parallelograms, they're a type of, or they're not trapezoids, but like they're trapezoids with more criteria because like both sides have to be parallel. Both pairs of opposite sides have to be parallel. So then you get like equal angles, equal opposite angles. And with one thing for parallelograms, you get that the diagonals also bisect each other. So we get that. Okay, how about we do this question? So the diagonals of EFGH meet at X. Find the distance from X to EF. One hint would be like if the list distance we're looking for is D, how does D relate to like the total height of the parallelogram? So this is H. Remember, you have like congruent bisected diagonals and equal and opposite sides. Oh yeah, by Bobby, you got the correct answer. Would you like to like explain to the class?
Yeah, so since the area is 56, so the height has to be 7.
Mm-hmm.
So I just thought that, so like from X to EF, I think it should be like half the height. So I
Mm-hmm.
got 3.5.
Very good. So again, we have like this is one half of the whole height because again, like these two triangles are congruent, right? So because triangle BXF is congruent to triangle GXH by like we can do SSS. So that means their altitudes must be congruent. Okay, very good. Now let's do rhomba. So if all four sides of a quadrilateral are equal, then the quadrilateral is a rhombus. So I should probably erase. Okay. So because all four sides of rhombus are equal, it is also a parallelogram because the parallelogram's only condition is like the pairs of opposite sides are equal. So this is even like this is an even stronger like satisfying. Okay. So that means like the area of a rhombus is fairly easy to calculate. If this is A, B, C, D and they meet at like E, Then triangle ABE is congruent to triangle CBE, congruent to triangle CDE, is congruent to triangle ADE, right? Because since it's a parallelogram, the diagonals are going to bisect each other. But because the sides are also equal, then these four triangles are all equal, right? So because of that, then you have the area of ABCD is equal to BD times AC over 2. Because these are all equal, these are all going to be right angles. Okay. Yeah, let's just move on to rectangles and squares. So rectangles. I'm sure you guys all know what rectangles are. They're just right angles, right? So like let's do one in some problems. Okay. Let's do a harder one. Um, AB equals 1 primary area. Yeah. So like G and F are on diagonal BD, and like it's inscribed. So like H and F are also on sides CD and BC. A hint is I would set this equal to X and then try to see if you can solve an equation for X. So like usually try to find two things that are like find two ways to represent one thing and set it equal to each other. Okay, so as I've written out here, I'm going to write BD two ways and set it equal to each other in terms of x so we can solve for x. So BD, as you can see, if our sine length is x, then GF is also x, right? And then BD, so because it's a diagonal of a square, then BF is also x because this is a 45, 45, 45, 45, 90 isosceles right triangle. And also this is also x. So BD is going to be 3 times the sine length of the square. But it's also equal to, as we can see here, we can write it in terms of these relationships, right? So as I'm doing now. Oh, wait. But we don't actually need to do that. Hold on. Because we're given side AB is 1. So we can just, this is equal to square root of 2. I forgot the question. So because AB is equal to 1, BD is equal to square root of 2. All right, any questions? Okay, let's go on to polygons. Okay, I don't think I have too much to say about polygons, but it's just that, so if we have any, like, n-gon, which means that it has n sides, n angles, then the sum of, like, all the interior angles is going to be that. This is because we can, like, separate it into n minus 2 triangles. And then every triangle has interior angle sum 180. So we multiply by 180. Okay. Um, for regular polygons, it gets a little more interesting, especially for regular hexagons, because regular hexagons show up like all the time, I feel like even in really hard questions. This is because they're really nice because when you like draw their diagonals, it will intersect at one point, and these are all equilateral triangles. Right, so this is S. The area of an equilateral triangle is equal to S squared of 3 over 4S squared. Right, so that means the area of the whole entire thing is going to be equal to 6 times that, which is this. You can memorize this, or this is just a nice formula that you can like derive on the spot, and it will help a lot. Also, if you have like a hexagon, you can like connect these, and then this will be a square, right? So sometimes that will help because you get a lot of 30, 60, 90 right triangles. Okay, so let's solve one question. Mm, okay, exactly 3 of the interior angles of a convex polygon are obtuse. What is the maximum number of sides of such a polygon? So like let there be n sides. Okay. Does everyone understand why I wrote this? Okay, because the sum of all the angles, as we went through before, is this, right? But because there are like 3 angles that are obtuse, the sum of those 3 must be less than 3 times 180. Right? Because obtuse angles are like, they can be greater than 90, but they have to be less than 180. And then the rest, which are the n minus 3 angles, they each have to be less than 90 degrees. Right? Because that's the definition of an acute angle. So that means like the sum of all the angles has to be strictly less than this sum. And this inequality is necessary and sufficient. It's necessary because of what I just explained, and it's sufficient because there are like no other requirements, right? So if we solve this inequality, what do we get?
I think it's n is less than 7.
Yep, you be correct. So that means like the maximum number of sides is 6, right? All right, any questions? All right, so now on to angle chasing. Okay, angle chasing just means that sometimes you're given a very like complicated diagram, and then if you want to prove, this is like more prevalent in proof questions, but if you want to like prove some things, sometimes it'd be really nice if you can prove if some angles are congruent. And then you can get like similar triangles or congruent triangles, and then you're one step closer to proving what you want. So be this list of tools, just feel free to take note of. They're just like important key parts of questions that very likely will help you solve a or get closer to solving a question. So like sums of angles, well, you'll know what they mean if we do like a couple practice questions. So sum of angles, triangle. So triangles are made, and you want to see like what are equal. As we can see like from the very first question, we were able to sum angles together, right? Because 70 plus 60 plus 50 equals 180. And then angles in a quadrilateral works the same way. Intercepting arcs just means like these arcs. And then angles around a point, angles in a right triangle, they add to 90 degrees. Inscribed angles subtending the same arc, they have equal angle measures. Angle bisectors, isosceles triangles, as we saw, if you get any equal angles within a triangle, then you can get isosceles triangles or an isosceles triangle. And then equilateral triangles are just if you get all equal angles in a triangle. And the vertical angles are self-explanatory because they're obviously equal. And then similar triangles, congruent triangles, as I said before, parallel lines and perpendicular lines are very good. One thing about exterior angles, so we said that the sum of all the interior angles is this, right? But sum of all the exterior angles is always equal to 360 for any polygon. And they're just the angles that you get when you like take the supplement of all the interior angles. Okay, let's do one question. Um, okay. Okay, so in the figure, PA is tangent to semicircle SAR, and PB is tangent to RBT, and then SRT is like a straight line. So, and then minor arc AR is equal to measure A, and then BR is equal to B. And we want to show that angle APB is equal to C plus D, and this is C and D. So C, this is like a proof question. So it'll take like 2 minutes. A hint I would say is connect like the points A to the center of the circles. So call them like points C and D. And that forms a polygon. So try to do something with angles. Anyone have any thoughts? Wait, so because of the semicircles, we have like the angle measures A plus B plus C plus D is equal to 360 degrees, right? Because this is A and then this is C, so A plus C equals 180, and then this is B and this is D, that also equals 180. But from pentagon PACDB, we also have A plus B plus 90 plus 90 plus angle P is equal to 540 degrees. Right? Because the pentagon has 3 times 180. If we subtract like 180 from both sides, we get that A plus B right? So what does this look like? This equation and this equation. This means that APB must equal C plus D, right? Okay, anyone have any questions? Oh yes, sorry. By Bobby, sorry.
So isn't like A the arc, kind of?
Yeah, so A is like the measure of this arc. And when we say that, we mean like the measure of the central angle.
Oh, I thought it was like the measure of the arc.
Oh, okay. Yeah, I can see why that can be confusing. So yeah, when you usually say like arc AR, that means the measure of the central angle that subtends that arc.
Thank you.
Welcome. If we wanted to say like the sector length or this arc length, we'd probably say like arc length. You'll see in questions, this word will be used. Okay, now let's go on to one of the last parts. So areas. Um, so same base altitude, this is quite simple, right? So if we have like two triangles that with the same base, it's clear that the areas are going to be equal, right? Because they share the same altitude. And you can kind of see this, and a lot of the times if you have medians within a triangle, then you'll get that these two areas are equal, and that'll be very nice. And then let's see, similar shapes. Sometimes you'll get like the midline of a triangle, and these are all parallel. So like this is parallel to this is parallel to this, and then this is parallel to this. So this interior triangle has area 1/4 of the whole big triangle. This is kind of bad notation, but like, yeah, because these are all parallelograms. So this is a parallelogram because again, these are parallel, and this is a parallelogram, and this is also a parallelogram, which means that when we take the diagonals, they partition them into triangles with equal area. So that means these 4 triangles all have equal area. And this is only for like the midpoints of the sides. Okay, and lastly, for complicated shapes, let's just do a practice problem, because it's very hard to explain. Okay. Find the shaded area given that so AB is diameter of semicircle And this line is just part of the circle that's like a quarter of the sector, so ACB. So I hope the question at least makes sense to everyone. So like this is like the area that's part within the semicircle, so ABC, but it's not including like the area that's bordered out by like this arc AB. Oh, sorry, I didn't give you guys lengths. My bad. AB is 2√2. Okay, so my suggestion for doing complicated area questions like these are to find basic areas that you can find and then see how you can piece them or add them or subtract them together to get the area that you want. So the area that we want is the shaded area. And then the shaded area can be found by subtracting the little like crescent area from the big semicircle, right? So those are the two areas we'll find. So the big semicircle is equal just to the area of half a circle, right? So it'd be pi times √2 squared over 2. And then the little secant part, which is like A, B, and then little secant part, that's like a bit harder to find. But we can find that by subtracting the triangle from the quarter circle, right? So what is that? So the quarter circle has area pi times 2 squared over 4, and then subtracting the triangle area is 2 times 2 over 2, right? So then we'll have it. So as long as we subtract this from this, then we'll be good. You guys can do like the arithmetic later if you want, but that's like the general idea. Does that make sense? So we find like the big semicircle, we subtract out this little part, but to find this little part, you have to subtract this triangle from the quarter circle. Yes, Vaibhavi, I think your answer is correct. All right, So if no one has any questions, then I think we'll be done. These are just blank slides for exercises, and we already did those. And then I think I'll move Power of a Point to next week's geometry class because it connects a bit more with next week's. So I'll post these slides in the recording right after class. So if you guys have any questions, you feel free to ask them, but if not, I'll see you next week.
Thank you.
Thank you. Bye.
You're welcome.
Bye.
Bye-bye.
Bye, thank you.
Bye.